You can start. Thank you.
Okay. Thank you very much. My name is Troy Raen. I'm a grad student at the University of Pittsburgh working on the Pitt-Google broker. Michael Wood-Basey is the lead on this project and is faculty at Pitt. Daniel Parafort and Christine Mazzola are my fellow grad students at Pitt, and Ross Thompson is a solutions architect at Google. The motivation for building this cloud-based broker was really to collaborate and make the whole process of data access and analysis easier for consumers and developers. We have a low barrier to entry. Those who want to do something simple will be able to do so quickly, and also support for power users. We are providing access to the alert data at every stage of our processing pipeline. And so you will be able to hook in anywhere and run your own analysis in parallel to ours. The choice to deploy in the Google Cloud also means that their full range of cloud computing options is available to users, which has many benefits. We have a deployed prototype that ingests ZTF alerts, stores the alert packet in a Google Cloud Storage bucket, and uploads the metadata to a BigQuery database. It also publishes pub substreams here and here when each stage of the processing is complete. Anyone can use these streams to hook into the data at any stage of the pipeline. PubSub is a similar product to Kafka. So this is our current status. We are working towards filling in the rest of this. Let's start at the bottom. We will provide the full replicated alert streams to anyone who wants it. We will also provide a stream that is semantically compressed so that it can be more easily distributed to and handled by a large number of users. Eric Bellum talked briefly yesterday and more in depth at the recent project and community workshop about LSST exploring a semantically compressed notification stream. We would redistribute that stream, and in that case, we may not need our own compression module here. But if for whatever reason LSST does not go forward with that, we would implement something similar. There are several things in this value-added products box here. These items in the box on the left will be separated into their own modules as we develop them. I will talk briefly about at the end about classifiers being developed by members of our team. For now, I'll just mention the cross-matching. We will cross-match across surveys and wavelength. And we will port public surveys and data sets to the Google Cloud, bringing it next to the LSST alert data and into a uniform format to facilitate the cross-matching. Again, notice that pub substreams are published when each stage of processing is complete. So for example, if you are a variable stars person and just want all alerts that match to a Gaia source, you can listen to the stream indicating that the alert has been cross-matched with Gaia and spin off your analysis from there in parallel to our own. Our data products take three forms. You'll have access to the raw alert packets, including the postage stamps. We will maintain a public alert database for those who have interests on timescales of hours to years. And we will publish several categories of PubSub messaging streams. So these are the replicated and semantically compressed streams, streams resulting from our value-added products and filtering, and streams indicating that an alert has passed a given processing stage. In terms of data access methods, you can query the database using SQL. You can connect directly to PubSub streams, and we will have a Python API and Tom service. We also have a web front end that I will preview in a few slides. One of the next things that I anticipate doing is to deploy a publicly available Supernova classifier. Here are the basic steps that I anticipate taking to do this. To deploy your own analysis, you could do something very similar. First, we listen to the PubSub stream at a chosen stage of processing. In this case, it's the very first stage indicating that a new alert is in the cloud storage bucket. Next, we load the alert metadata. The details of this particular step may be different for users outside the Pitt-Google broker, but everything else here should be the same for you as it is for us. Third, we run a filter on the metadata to select likely extragalactic transients. This is just a Python function. Next, we pass this to the classifier, let it do its thing. And finally, we store the results in BigQuery and publish to a pub subtopic. These processing steps will be packaged as a Google Cloud function. These cloud functions allow you to deploy bits of code to the cloud without having to deal with any server management. This is probably the simplest cloud computing option in the Google Cloud platform. You will also have other options as well, including spinning up your own virtual machine. As with all of our software, as we develop, we will write documentation to guide similar development by users. And so this process will be fleshed out with actual code samples and things you can use to write your own analysis. We have a web front end that is currently in development. This is a screenshot of our deployed prototype showing a basic filter and a list of recently ingested alerts. To end, I will touch on two classifiers in development by members of our team. First is a template-based Supernova classifier developed by Daniel Paraford to separate out 91BG-like objects. These look similar to standard 1A supernovae, but they are different enough that it will be important to understand the distributions to get a better handle on how they may affect supernova cosmology. The classifications are based on relative model chi-squareds in bluer and redder passbands. The 91BG-like objects tend to end up in the upper right quadrant in this space. If you're interested, you can read more about the method in Daniel's paper, which was recently accepted. This can be deployed as a cloud function, which I discussed earlier, that runs in parallel with the other analysis. And the modular design of our broker would simplify the move between running this on the real-time alert stream and running against database queries. Finally, I have been working on a classifier using a method called a Bayesian belief network. The goal here is to model the causal relationships between the available and the relevant information in a way that makes the inference tractable. This is not a neural network. The arrows in this diagram do not represent the flow of data. They represent causal relationships between the nodes. Information can flow in either direction. Thank you. We use the network structure, the learned probability distributions, and a set of priors to calculate the probability of a certain class given the other available information. I envision a similar Bayesian belief network that would function as a meta classifier for our broker. To explain what I mean, one way to think about this is as a machine learning model stacker, where we run various disparate light curve classifiers. So for example, one for supernovae, one for variable stars, and so on. And then fold in these other important properties to produce classification probabilities in a principled Bayesian way for a wide range of objects. To get started, I'm working on the version shown here, specific to finding calcium-rich gap transients. These are transients that exist in the luminosity gap between supernovae and novae. They show significant calcium lines in their spectra, and importantly here, they tend to explode in the far outskirts of their hosts, on order of tens of kiloparsecs from the center. There are only a handful of calcium-rich objects observed to date, and so I would start with a much simpler network than what I've shown here, perhaps just the class and the galaxy offset to build a toy model. And then as we observe more and more objects, we can add in complexity to the network. And with that, I will end and take any questions.
Thank you, Troy. Guille, there are a few questions I see.
Yeah, we have a lot of questions for Troy. So the first one comes from Slack, from Julian Peloton. Can you expand on the semantically compressed stream you mentioned?
Oh, so this is something that was envisioned from the beginning by Michael Wood-Vasey be able to, so let's see. So the costs in the cloud computing model often depend on ingress and egress and data processing. And so if we can reduce the size of the alert packet by a factor of 10 to 100, the full alert stream, or at least a large portion of it, can be distributed to more users, and the users will be able to handle it easier. In terms of exactly what's in that stream, I know that Eric Bellum had a good list on slides from his presentation at a previous workshop. We don't have a specific, I don't have a specific list for you, but that's something that's very much open to discussion and input. And so we certainly welcome input from anyone with an interest into what should be in that compressed stream.
Thank you. So please have a look at the Slack, and again there will be a long discussion session on brokers in the afternoon.